now we have a model for our charged rod. So now we need to calculate the field. So let's start just by drawing the rod again, a little bit smaller this time. And we have a nice straight rod like that. And we want to calculate the charge at a point P on the axis of the rod, but a little bit to the side. The rod has a property, lambda. That's its charge density. Like we talked about before, that's the number of coulombs per meter of charge on this rod. It has a length L, so at this point we need to set up a coordinate system. So let's imagine that the rod is sitting on the x-axis. So there's plus x, and there's minus x, and let's say it's sitting right at the origin. So I'll go ahead and draw the y-axis here, even though we're not going to need it in this 1D problem, but there's the origin right there. Therefore, we know that the rod, if it starts at the origin, makes it to a point here that's the position x equals L. So that would be the basic setup to start the problem. We also need to know the distance that we have here to the point P. We'll call that A. Like that. All right. So the question is simply, what is the electric field at point P? Now we've set this up to have a continuous charge along an extended object. Suddenly we can't use Coulomb's law anymore. In Coulomb's law, you say you have some charge here, it's at a distance r, and you write Coulomb's law. Well, here we have charge at a big range of distances, right? Some of the charge is really far, some of the charge is really close, some of the charge is in between. So suddenly we can't just do a straightforward application of Coulomb's law. So let's do this. Let's consider a small piece of the rod. So let's just say, instead of thinking of the whole rod at once, let's just grab a little chunk like this. And we can call it dx, a small piece of the rod dx. And then that small piece of rod will be at a specific place. And we could actually apply Coulomb's law. This dx is called a differential element. Okay. So this is our way to deal with a continuous system as we break it up into a little small piece. Okay, so I see we have a question. Let's see. Oh, Tom Cruise taking the class, not bad. We had point charges, then we made a smooth model, and now point charges again. What's the deal? Okay, yeah, so that's actually true. I hadn't really thought about that. Is we started with, we said the rod has little individual electrons, and that would be too hard to deal with. Right? So we made it a smooth continuum, and now to deal with the continuum mathematically, we have to break it up, and that's actually true. Mr. Cruz is correct. The difference is this is a smooth continuum, and we're going to actually shrink this thing down even smaller than the spacing of the electrons. So I think my answer basically is you'll see in a minute. Okay? On the next board, you'll see the difference between thinking of electrons and thinking of a differential element. Because let's go ahead with what we can do with this is this differential element, dx, it creates a differential field that we will call DEP. Okay? So we're looking for the electric field at P. That would be electric field P, and we just put the D in front of it to remind ourselves that what we're really about to write down is just the little piece of the field that's created by the little piece of the charge. Okay? So that's DEP. So let's write it down. Let's write it down. Now this is Coulomb's law, right? This little guy is at a set distance from P, so we can actually write it. So that's KE. What goes up top is the charge. What is the charge in this little dx? Well, we'll just call it dq. The rod has a total charge q. You can figure out what it would be. It'd be lambda times L. This little thing is dq. The separation of this one little piece, that gets a little tricky. You've got to think about it. It's this far away, A, plus this far away. Well, what is that? That's the length L, but we've moved over. The point dx is at a position x. So we've kind of moved over there. So that's basically L minus x. So it's a plus L minus x squared. And then we got to think about the direction. And in this case, all the little elements are along the x-axis, and so is the point P. Therefore, all the field will point on the x-axis. So we're lucky in this case. It's a 1D problem. To deal with the direction, all we got to do is say it's in the I-hat direction. It's always going to be on the x-axis. We'll worry about multiple dimensions later. Okay? So we got our DEP. Let's keep going.